Okay, in a previous video, we had looked at the differential equations and their solutions and equations that weren't solutions to them. And we found out how to prove that something is a solution or is not a solution. But we haven't yet looked at how to determine what a solution is or looks like in the case when we've been given the slope field. So if we've been given the differential equation, we can, if it's first order, we can draw a slope field. And from there, we should be able to work our way to what the answer should look like using a numerical method called Euler's method. So let's cover that now. Okay, so we have our differential equation that we had before, that dy dx equals x minus y, and we have the corresponding slope field underneath. Okay, so Euler's method for determining what the solution looks like is a numerical method where you take steps, a little bit like using a Riemann sum, right? So in the first case, we're going to take fairly large steps. We're going to let delta x equal plus or minus 1. We'll start with plus 1. But then we'll go in the negative direction. We'll start at a point that's on the in the field. We'll start at the point 0, 2. So this will be our initial point. Remember the initial value problems. And we need to figure out how to step our way through the field. All right. So we're going to start right up here at 0, 2, which is approximately there in the graph. And we're going to try to work our way following the slope field that will give us the direction we should be heading in. Okay, because remember the slope of a line tells you how steeply it should point. Okay, so we have a downward slope in the field here, so we expect to be heading downward. All right. Well, we're going to follow an algorithm here. We'll first compute delta y by, pardon me, looking at the slope, which is in calculus is dy dx, times delta x. Then, to determine a new y, we'll call this y of n plus 1, the next y. We'll take the y that we're on and add delta y to it, all right? Now, this is a time-consuming, tedious process. So let's just step through a little bit of it. I actually worked it out on a spreadsheet because this is mind-numbingly boring to do for too long. But we need to understand what it is that the computer does. So we're starting with x values and y values of 0 and 2. And so then we know dy dx from the formula off to the left must be negative 2. So how do we find the next x and y value? Well, we've already said x should go up by 1. Okay, what should y do? Okay, well, we need to find what delta y is. Based on our little formula, we take the slope. We know that y should be dropping by 2 units every time x goes up by 1, and you multiply that by delta x, which is 1, and so that gives you negative 2. All right, so if that's a negative 2, then we should drop by 2 from where we were, which was 2. So that brings us down to 1, 0. All right, and if I draw my little hash mark lines, I'm guessing 1, 2. Whoop, oh yeah, we can go line up. That is 1, 2, 3, 4, and 5. So 1, 0 is blue again, is right about here on the graph, right? So now we're at 1, 0, and we need to calculate a new dy dx, which will be 1 minus 0, which is 1. So now the slope should be 1. So delta y should be 1 times delta x, which is 1. So we should go up 1. So by the time x gets to 2, y should go up 1 from 0, which puts us at 1. And then we compute a new slope in just a moment. Okay, well, that'll be 2 minus 1, which will be 1 again. But we now know we're at the point 2, 1. So if I go over to where 2 is and I go up 1, that is right there. Now, this graph is very angular, okay, because we're taking big steps. So we should be following the slope field in a very smooth, curved way. Instead, we're taking big angular jumps through it, all right? So our answer is going to be a very rough approximation of what should happen because we're taking large steps. So by the time x gets to 3, we need to use this row to compute a new delta y. It's 1 times 1 again, which is 1. So we should go up to 2. And when we do that, 3, 2 is right there. You'll notice we're following that asymptote that I talked about before. The slope will again be 1, and so we actually just keep on going up this line all the way to the end, okay? So we're going in a nice straight line along the asymptote, but we know we probably didn't zig right to the asymptote. We should be approaching the asymptote and then getting nearer and nearer to it as opposed to traveling directly along it. Well, now there's another thing we can do. We should be able to go backwards. If we start at 0, 2 again, we should be able to head in the opposite direction. Well, to do this, delta x is -1. So delta y is -2 times -1, which is +2. So that means when we head in the next direction, the negative direction, by the time we get to x equals -1, y should be at 4. Okay, so we can go over to -1 and up 4. That is right about there. Okay, so looking at that, that actually will have the same slope as the line to the other side of the y-axis because we had a slope of -2 here going forward or backwards. Now we get a new slope, -1 minus 4 will be -5. So in the next step, we're going to go off the page. Delta y would be -5 times -1. We would have to go up 5 as we go back 1, so -2, 9. And we can stop there because we're going to just shoot off of the page. It's going to go up very steeply, something like that, and off of the page. Now we would expect if we, in these big chunks, we get answers that are not really quite what we would expect. We would expect that we kind of wrap around and follow the slope field. We'll talk more about this in another video to approach the asymptote on the right-hand side rather than having this sharp V-like structure. Well, how do we get closer to the answer? It's just like Riemann sums. We take smaller steps. So if we did all of the same stuff with delta x equal to negative plus or minus 0.5, we'll get answers that are better. So let me go through some of those quickly. I'm just going to calculate the first couple of steps and then just report what the spreadsheet gave me. So I just want you to be familiar with the algorithm. So we start at 0, 2, so dy dx was -2. So for the first step, delta y is -2, but this time the delta x is 0.5. So we only drop by -1. So by the time we get to x equals 1, we will drop by 1 unit and then recompute the slope, and the slope should be 0. Right? Oh, I am sorry. I made a mistake here. We're not stepping by 1, so the slope will not be 0. We're stepping by half a unit. Let me slide on up here. Allow me, yes. So we're half a unit, so now the slope is -0.5. Okay, so let's put those first 2 points on here. We're at 2, 0, which is about there. And then we're going to drop down to 0.51, which is right about there. So we have a short little segment like that, okay? And then we'll take another step. So we want to get to x equals 1. So to do that, delta y will be the slope, -0.5 times the step size in the x direction. So that will be -0.25. So we'll come down another quarter, which puts us at 0.75. And then we could recalculate the slope. 1 minus 0.75 should be positive 0.25. So we'll start going up in the next step. But for now, 1.75. So that's, let's see, so that was the first one. It's right here, and we're at 0.75. So I think that's about in here. Okay, so we're already, we can see we get a more curve by doing it this way, right? Now notice also as the slope gets smaller, we're actually looking at a much smaller line segment, and smaller line segments will give us more precise results. All right, so let's keep going. we get to 1.5. To get to 1.5, this will, we need to find a new delta y using the same method, and then we'll take a quarter is the slope times 0.5. So we're now going to go up 0.625. So that gets us to about 0.88. All right, and then I'm not going to keep showing this. We're going to get to 2, 1.19, 2.5, 1.59, 3, 2.05. All right, so if we go ahead and put those points on there, by 1.5, we're at 0.88. So probably more like there. So we're starting to head back up. By the time we go over another half unit, we're up at 1.99. So or 1.19. So we're up in there. And then by the time we get to 2.5, that'll be the next one over, we're up around 1.59. So I think that's right up in here. And so on. By the time we get to 3, we're up to 2.05. So that's right about there. All right, and we're going to get, you can see we're close to this asymptote now, but we curved much more nicely to it, okay? And that was just bringing the step size down to 1/2. Remember, if we want to go in the other direction, we would start at 0, 2. Slope is -2. And then the delta y is -2, but now the step is -0.5 in the x direction. So that comes out to be +1. So by the time we get to -1 in the x direction, we should be up at 3. So I'm sorry, -1/2. We're taking half steps. So -0.5. So by the time we're at -0.5, we're up around 3, which is right about in there. And then the next step, I think, will take us right up to the top of the screen, something like that. So you can see this is much closer to the curvy path that we thought we would get. If we want to get closer, we want even smaller increments. But you saw how long, and this took a long time just to do steps of 0.5. So if we were to divide that down to steps of 0.25, it would take, doing that by hand would take an extremely long time, which is why we switch over to using a computer if we want to figure out how to step our way using Euler's method through a slope field.